All right, so let's talk about the questions from the checkpoint for Module 3, all of which are talking about basically trying to attend to continuity and differentiability. So the first one here is talking about what happens to this function x equals -2. So draw a dashed line over that point. So basically, I want to ask two things here. Do I have continuity? And do I have differentiability? So let's handle those one at a time. So continuity. We have continuity at a point if, so we're looking at x equals 2, so let's just pull that in. The limit as x approaches 2 of f of x is equal to f of 2. Well, what is f of 2? F of 2 is equal to -2. Um, kind of colored over, but there's a dark dot right there, filled in dot. What is the limit as x approaches 2 of f of x? So if I approach from the left and the right, we'll see that we're kind of getting closer and closer and closer to y equals 0. So the function is defined at -2. The limit exists at 0. Those two things don't agree, so I can't have continuity. And one of the things we know about the relationship between continuity and differentiability is if we don't have continuity, we can't have differentiability either. So this function is not continuous. It's neither continuous nor differentiable at x equals 2. All right, same function, but now we're looking at this x value, x equals 2. So do we have continuity? Well, let's think about it this way. What's the limit as x approaches 0 of f of x? Well, that's equal to, if we approach from both the left and right, it looks like we're approaching a y value of -2. What is f of 0? That's -2. So that tells me I have continuity at x equals 0. But what about differentiability? So we're looking at a graph. We cannot have a unique tangent line at this hard corner. So because of that, I believe I have not differentiable at x equals 0. So we have continuity, but not differentiability. All right. Question 3 involves this function here. And again, I do want to know, do I have continuity and differentiability? So first continuity. What is g of, not g of 0? What is g of 1? G of 1 is equal to the square root of 1 minus 1, and that is 0. What is the limit as x approaches 1? And I'm going to say 1 from the right because this function is not even defined for values of x that are from the left of 1. What's the limit as x approaches 1 from the right of x minus 1? Um, well, if I have values of x that are close to 1 but just above it, then I'll be getting the square root of very, very, very small numbers. Those will all be defined because they're positive, and if they're very small, that's going to trend towards 0. So I believe I have, hopefully you'll permit me abbreviation of just continuity. I have continuity. But what about differentiability? Well, differentiability all comes from this limit. The limit as h approaches 0, and I'll say from the right because there's there is no function essentially to the left of x equals 1. So the limit as h approaches 0 from the right of g of x plus h minus g of x all over h. What is g of x plus h? That'll be the square root of x plus h minus 1 minus the square root of x minus 1 all over h. And again, I forgot my limit operator. Limit as h approaches 0 from the right. We have square roots here. I am going to use the conjugate to try to deal with those. So I'll multiply both numerator and denominator by the conjugate. So it'll be square root of x plus h minus 1 plus radical x minus 1 all over the same thing. Radical x plus h minus 1 plus radical x minus 1. How does that simplify for me? So the limit as h goes to 0 from the right of the numerator. Why did I use the conjugate? Basically to deal with these square roots. And knowing that since I use the conjugate, the inner terms are going to cancel. So what do I get? I get x plus h minus 1 minus x minus 1 all over h times the conjugate. X radical x plus h minus 1 plus x minus 1. So what happens in the numerator? Hopefully I get some things that cancel for me. And it looks like the x's are going to cancel and the 1's are going to cancel. So I have h over h times the conjugate, radical x plus h minus 1 plus radical x minus 1. So from here I get the limit as h approaches 0, the h's cancel. So 1 over the radical, oh, there's one detail that I forgot to include here, but I can do it now. Radical x plus h minus 1 plus radical x minus 1. Keep in mind here, we're not looking for the derivative everywhere. We're looking for the derivative at x minus 1. So if I basically, instead of trying to evaluate this for any x, evaluate it for just x equals 1, then we can transform this expression a little bit. The limit as h goes to 0 from the right of 1 over the square root of 1 plus h minus 1 plus the square root of 1 minus 1. So what happens here? A lot cancels out. The limit as h approaches 0 from the right of 1 over, so this right-hand radical, that'll go to 0. This left-hand radical will just go to radical h. So can't really simplify this anymore, but what I have is, what's going to happen to this is h goes to 0 from the right. Well, the numerator is going to get, or the denominator is going to get closer and closer to 0. And dividing 1 by that is going to give me very large numbers. So this limit actually goes to infinity, which is another way to say the limit doesn't exist, or a very specific way of saying the limit doesn't exist. So in this case, I have continuity, but do I have differentiability? I do not. The limit definition of the derivative does not exist. And finally, free response question, I want you to draw me a graph that meets all these conditions. It's going to be pretty quick. I'll tell you because you cannot do this. We saw from another example, or our past example, you can have continuity at a point without having differentiability. So that can be done. You can also have points where you have neither continuity nor differentiability. But this middle bullet here, if you're differentiable at a point, if your function is differentiable at a point, it must also be continuous there. That's one of the ways that differentiability and continuity are related. So the idea that you can have a function that's differentiable at a point, but not continuous there, that is completely impossible. So this graph can actually not be completed.